Yeah, hello everyone. So not so many survived. A lot of people, they were hungry apparently. Don't judge them, I'm also a foodie myself. And as a reward for you, there's gonna be some food also in the presentation. So yeah, stay tuned. So hello everyone, my name is Eleftherios Mylonakis. I work at MindPeak. And today I would like to show you how you can achieve reproducible ML workflows in cancer diagnostics. Maybe also after a short demo, maybe you can take it at home to your companies or to your personal projects. So first, a few words about MindPeak. So our main mission is to build better AI for custom diagnostics. We are proud to say that we have diagnosed more than 50,000 patients to date with our 11 diagnostic algorithms. We're also really happy to claim that we have the first ever AI in pathology, in diagnostic pathology in the US. And also for the fellow scholars, you can also find us with our scientific publications, as we have 20 plus peer-reviewed ones. So I would like also to give you a small intro into pathology. So usually when a patient has cancer, what they do to him, first of all, they identify, of course, the organ that has cancer, and they take a biopsy. A biopsy is like, with a needle, you take a small piece of the organ, which then you cut into really thin slices. You mount it on a glass slide. This glass slide is similar to what you had in biology classes. And, yes? Better? Yeah, I should, the mustache was not a good idea, yeah. One day before. Okay, yeah, so you mount this, this tissue on the slide, and you stain it, and you stain it with specific chemicals that make specific also cells to prevail. And then this slide, it's been put under the microscope, and it's been examined by the pathologists. And usually, each case, it takes around 2 to 30 minutes. And it takes so long because these images, they're huge. They're actually 100,000 by 100,000 pixels. And we claim, and we proudly say that we have a world-class pathology AI, and this study that you see on the screen proves it. Basically, what happened in this study, a group of pathologists, of specialist pathologists, they came together, they assessed some cases in order to find a common ground truth. So basically, they define a golden ground truth. And then they put under the test not only different companies, so the solutions of the companies, but also individual human pathologists. And as you can see, MindPeak performed the best with 88% accuracy. And the really reasonable question is, how do you get there? So in order to get there, I mean, an obvious thing is that you need data. Actually, you need a lot of data. And you need also a nice group of ML people with a lot of skills. Two of the most important is the scientific way of thinking. So for example, to design hypothesis-driven experiments, but you also need diligence, which unfortunately, in my opinion, it's been usually not taken so seriously like the left one. And why do you need diligence? In order to avoid pitfalls. So imagine this scenario that you have trained your statistical model. You have achieved a really good accuracy, 96%. Spoiler, this never happens to us. It's not so high, but for the sake of demonstration, I'm going to show you such a high number. And but you're so happy for this statistical model that you don't care about the data that you trained on. You're like, okay, this model, it's great. It's never going to be replaced. It doesn't matter how I trained it. Then after 6 months, you sit on the desk, and boom, you get another model that achieves 98% accuracy. Then you go back to your colleagues, really happy to claim that you achieved a better model. But of course, your skeptical colleague will say, I'm not sure if I can compare these two models, because, for example, maybe you evaluate it on different test sets, Or maybe the second model, it was trained on patients from the previous test set, so there's a data leakage. So yeah, this is a really nightmare scenario. So in order to avoid these pitfalls, you need to track your AI development. What does it mean, tracking AI development? It means tracks your raw data. That means, in our case, our images, the annotations. So we have some pathologists annotate these images. So we also need to track this. We also need to track our methods, our architectures, the whatever code we're using. You also need to have a nice an experiment registry. You also need to track your evaluation methods. And also, this something that can enable you to track this AI development shouldn't hinder you, shouldn't make you slower. It needs to make you faster and faster. And I want to reveal this tool, but first, I would like to make a small break to make some palak paneer. I don't know how many people are familiar with palak paneer in this room. Palak paneer is this delicious Indian dish. In order to make this, you need your ingredients, of course. The ingredients, they're such as spinach, that's palak, that means palak. Also, you need paneer, which is this delicious Indian cheese. Of course, you need a lot of spices, because it's an Indian cuisine, and many other stuff. You need your cookware. So, for example, something to boil your spinach, something to make the spinach into a nice paste, and you also need a frying pan to fry your paneer. And last but not least, you don't only need your recipe, but you also need these fine recipe details that are gonna make your final dish amazing. So for example, the amount of each ingredient is really important, because if you put too much chili, it's gonna get super spicy, but if you put not so much, then it's gonna get blunt. And I did that the other days, this super realistic image. I cooked this for my girlfriend. She was really happy. I was really happy. I was really surprised by the result. So happy that I did that on a Monday. And after 2 weeks, I decided to do the same. And unfortunately, the result was not so great. And I'm here today to find out together what went wrong. In order to find what went wrong, we need to agree on something. We need to agree that kitchen is reproducible. So basically, what does it mean? It means that if on Monday I take my ingredients, my cookware, and my recipe, and I make a dish, if on Tuesday I take exactly the same things, I'm going to end up with the same dish. But if I take exactly the same things and I remove a little, like even a spice that I used in the previous days, I'm going to end up with a different dish. Okay, but enough about cooking. I'm pretty sure you're hungry already. And this is code.talks, so let's go back to machine learning. But actually, now that I think about it, machine learning and kitchen, it's not so different, right? So instead of your raw ingredients, you have your data. In our case, the data is these images with some annotations by our expert pathologists. Instead of your cookware, you have your code. And instead of your recipe details, you have your small knobs, your hyperparameters. That's how we call them in machine learning. And of course, the final dish is your final model. And in order to control the outcome, so the final model, you need something to control your raw data, the code, and the configuration. And this something for us, it's a tool called DVC. So we use DVC. I want to tell you why you should as well. So what is DVC, first of all? DVC stands for Data Version Control. It's an open source tool that you can use for data management, pipelines definition, and experiment tracking. As I said, it's open source, so you can find it on GitHub. It's getting really popular already. And you can also find their documentation page. It's pretty well documented. Whenever I have questions, I go there. And how does it work under the hood? It works really similarly to Git. And not only that, it also has a really nice synergy with Git. So in traditional projects, like code projects, you have in your environment, you have your local code. And then you can version your code with Git. Most of the people, I hope that you're familiar with Git. Otherwise, this doesn't make sense. But yeah, you can version your code with Git, and you can have a Git remote where you can push your code. This remote, it can be whatever you want. This Git server, it can be whatever you want. It can be GitHub, GitLab. But unfortunately, in data science, we don't have only code, but we have data. And in our case, we have really heavy data. This whole slide images, they're 100,000 by 100,000 pixels, so they're gigabytes, is one of them. And this data, you cannot afford pushing them to Git. So what DVC does, it creates a separate storage. The storage can be whatever you want. It can be an S3 bucket. It can be in Google Cloud. It can even be another computer in your local network, which you can connect through SSH. And it offers similar commands like Git. So for example, DVC push, DVC pull to interact with this remote. And then you need a final thing to connect basically these two, the code and the data. And this is the .dvc files. These are basically artifacts that they represent the actual files in your local environment. So now I would like you to show you a small demo of how does it look like. Here I have set it up. Okay, let's see how this works. So I have created a really small repo. And the main goal of this repo is to create a model that solves the following problem. Let me open this in a convenient way. So we're gonna work with tabular data. So that means with a CSV file, and each row it represents one patient. And the goal is for each patient to predict the final diagnosis. The diagnosis is a binary problem, so it can be malignant or benign. And you can do that by combining the features, the following features. The features are cellular features, but this doesn't matter, just for your own information. What I have, apart from my data, I have my code here. And I have basically 3 files. The first one is splitting the data. So I want to split the data into train and test. With the train data, I'm going to train my model. And with the test data, I'm going to evaluate my model. So the other 2 files are about this. So basically this one, the train model. With the train model, you can train the model, and you can evaluate the model on the test set. And something that's important for DVC, let me close this. It's this DVC YAML. And in this DVC YAML, you can define basically your experiment pipeline. So as you can see here, there's 3 stages. The split data, the train model, and the evaluation model. This is equivalent, now in this case, it's equivalent to the code that I have. And let me show you really quickly how does it look like from. So with DVC, usually you interact with it through the command line. And I can run, for example, DVC DAG, and this will give me a dependency graph. So DVC knows because I have defined it in a correct way. It knows that first comes the splitting the data. Based on this data, you can train your model, and based on so the train of the model, it has as an outcome, it has a final model which you can evaluate. And I also will expand one stage here. So the format is the same also for the train model and evaluate model. So I'm gonna show it just for the split data. And this stage, it has 4 main components. So the first one is the command. So for example, here I just run this Python script of splitting the data. This, by the way, DVC it's agnostic, so you can use whatever you want here. You can use other languages. You can even use bash scripts, whatever you want. Then you have the dependencies. So these are basically the inputs of the stage. And that means that if you change one of the inputs, then this stage is invalidated and you have to retrigger it. Apart from that, you also have some parameters. So for example, in this case, you have the test size, how big your test set you want to be. And again, the same applies also for the parameters. So if you change the test size, then you need to rerun the stage. And last but not least, you have also the outputs, which is the output of the stage. In this case, there are just 2 CSV files, which are a result of the first CSV split it into 2. Okay, and now we can basically run already our first experiment. No, sorry, one more thing that we also need to check is the final thing, I promise. It's the params YAML. And in this params YAML, you can define the parameters of each stage. So for example, here for the splitting data, I can increase my test size. Or for my train models, I have different parameters. In this case, I decided to go with a random forest. So you can manipulate this parameter as you wish. So I would like to run first an experiment with the default configuration to see what we can achieve already. So, so this basically, this command, it says tvc experiment run, so run the whole pipeline. And the -f, you can ignore it for now. It's because I have run it already, and I want to force to run it again. That's why it's there, but don't worry. And let's also give it a name to code.talks first exp. So what happens under the hood? Let me show you. So each stage has been run. So you can see here, first it runs the splitting data stage. It does some stuff. These are output from the Python script. Then it runs the training model. And lastly, it runs the evaluation model, which you can see here. And now I want to see my final results in a nice table. And for that, I have my dvc exp show, which basically show a nice table with all the metrics that this experiment has achieved, what parameters they were used, and what code was used. And you can see, for example, this experiment was created here. We achieved a test accuracy of 0.83. Also, if I scroll to the right, I can see what configuration I used. Even more to the right, what code I used. I can also now rerun this command with another name to see what will happen. So dvc exp run again. I'm going to remove now the -f. I'm going to run it with under the name code.talks second experiment. And dvc is smart enough because it tracks the inputs and the parameters and the dependencies. It's smart enough to know that actually none of the stages need to run again because I know already the result. So if I go now again to my table with dvc experiment show, I can see that it was created here. Of course, it's identical to the previous one, but I can really compare it and I can really confirm that nothing changed. So now I would like maybe to help me to do some data science work. So who is familiar here with random forest? Is anyone familiar with? Don't be scary. Okay. Maybe you can, we can do it randomly. Is someone feeling lucky? No? Okay. You're feeling lucky? 3? What 3? Okay. Good. So I save this. I can do now. So okay, my friend now he did. Can you also give me your favorite fruit? Banana. Okay, I was expecting it. Okay. So so now I can use the command dvc status. Oops, sorry, typo. dvc status, and with this command I can see what it was changed, and yes, indeed, the train model number of estimator 3 was changed, and I can run again my experiment. Let's give it name banana. So because again, so let's scroll up. This is really fast. Again, we didn't change the splitting data at all. So dvc is smart enough to not retrigger the splitting data, but we changed something on the training. So that's why the training was triggered again. And because the training was triggered, we have a different model. So we need again to retrigger the evaluation as well, which you can see here. So again, we run the evaluation model. Okay, anyone else lucky, or shall I try myself? Okay, no, I'll try myself. I will also increase the max depth to 3 because, I don't know, because I like the 3 number. And I will go with, you can guess it, apple for this case. Again, the same thing applies, so only the train model and the evaluation model runs. So if I do now again dvc exp and show, I can see my nice table that I have apple, banana, code.talks, all this stuff. And I have also my different metrics. So unfortunately, sorry, apple is a little bit better. Although my banana is also my favorite. So that's a payback. And let's say now that I'm really clumsy, right? So let's say that I do this carry command. This carry command, it basically means erase everything that it's not committed to your Git. So all the changes are gone. But so usually this is really bad because you really lose everything. But dvc got you covered because again I can do dvc exp show to see my experiment. let's say that, okay, for this case, I didn't want to go for apple, but I want to go for banana. What I can do dvc exp apply banana. And this will bring everything. So it will bring back the configuration. As you can see here, this changed to 3. This states, this max step that I changed, it stayed to 1 because banana only had 3. Also, it checks out all my data. So basically, the model that was produced during this experiment, also it's been checked out under the folder here. So yeah, this was the demo. So just a really small recap. So we wanted a tool to track our data and our annotations. We have this. We want a tool to track our methods, our code, our architectures. We have this. We want something that enables us to have basically an experiment registry. We have this. We want also something that doesn't hinder us, but we want to have fast iterations. I think we also have this with this pipeline. And we want something that regulatory is really happy because if I release a model, I can really tell how I trained it in the end. So that's all. Thank you for your attention. You can scan this QR code to find this TVC demo, and I'm open for questions.